Yeah, I always got to have that little 3, 2, 1 thing. All right, so does this make sense? This whole how the t thing is being read and what it's really doing. Okay, it's very similar to the z stuff. It's just sort of giving you direct percentages based on the little subscript down on the bottom. So whatever number is the subscript next to the t, that's what area or what percentage you're looking to the right or left of your t value. All right? And again, if it's to the right, leave your t value positive. If it's to the left, make your t value negative. Okay? I think there was one question in the homework that asked you for what value of t is it where the area is to the left on a one-tailed test, and if you're looking for that, make sure that whatever number you look up, you make it negative, because notice that none of the numbers in the t-tables are negative, okay? And it's because it's assuming you understand the symmetry around a symmetric bell curve like this one, all right? Does that make sense? Okay, again, I strongly encourage you to potentially look at some of the odd-numbered problems, because the odd-numbered problems have the answers in the back of the book. So take a peek at some of those and see what answers they're giving, and then say, oh, that's what they meant, and adjust accordingly, okay? That should also help to get some of the answers, if this whole concept is not overly clear to you right now. And like I said, we will play around with this more in chapter either 8 or 9, one of the two, when we come back from spring break, where we actually start getting into calculating real statistical values. Not bad? All right, so let's review really quickly. What did we do in chapter 7 already? We did 7.1 and 7.2, but what did those mean? What were we doing in those sections? Yeah, we were dealing with central limit theorem and standard deviation, right? So the central limit theorem, which basically told us that we know how to work with sampling distributions. And guys, remember that a sampling distribution is a distribution of every sample you can take of a specific sampling size in a population, all right? And that one of the things that we learned is that the mean of the sampling distribution is the same as the mean of the overall population. Mean of a sampling distribution equals mean of the population.
I wasn't going to walk into the camera to fix it.
Checking. You could have done a song and dance if you wanted to. All right, and the other thing that we learned was that the standard deviation of the sampling distribution is equal to the standard deviation of the population divided by the square root of whatever sampling size you chose in your sampling distribution. All right? And those are powerful tools that allow us to start calculating probabilities when we actually start taking samples instead of just picking single values.
So what's the standard?
This is the standard deviation of the sampling distribution, right?
Then the other one would be just the sample, or the standard deviation.
Of the population, yes. So sigma with a little x is the sampling distribution standard deviation. And regular sigma, this is the population standard deviation. And again, just in case, we'll write it down just to be sure. N is the size of sampling distribution. And again, if you look in chapter 7 in your sort of formulas note card, these are the two formulas that it tells you are important from 7.1. It's just knowing that these two exist. All right. All right. That's at the table for what we did in 7.2. Right? So let's suppose that if I sample 100 people from a normal distribution with a mean of, whatever, let's keep it relatively simple. Let's go with 20.0 and a standard deviation of 4.0. What is the probability mean of my sample is more than, say, let's get a really rare one, 21. So the idea behind this is that if you know the population has a mean of 20 and a standard deviation of 4, and you just randomly grab 100 people out of that population, whoever they are, if you did it truly randomly, mind you, what's the likelihood that the average of those 100 people that you grabbed winds up being more than 21? Basically, an entire unit away from the mean. You wouldn't think that that's too far of a distance, right? I mean, if the average is 20, 21, getting to 21, that should be pretty easy. But remember, we're sampling 100 people in this population. So, I'm trying to find the probability that x is greater than 21. Again, that's the sort of standard process we've been doing all through chapter 6 and 7. Since I want to find a sample more than 21, x greater than 21, we want to convert this to z. Again, remember the way you convert your x's into z's is you subtract the mean and you divide by the standard deviation. And note that if there's a sample with it, you have to add the sample size into your calculation. And here's that sigma over the square root of n that we did back in 7.1. Same sort of concept, okay? What'd you get?
Z greater than 25.
25?
Oh, square root of 100. Never mind.
Yeah.
Do math. Still pretty good.
2.5. Yeah, 100. That would be if we sampled 100,000 people. Then that's, yeah,
Still pretty big.
true. 2.5 is still a pretty big number. And again, and how are we going to calculate z greater than 2.5, folks? Exactly. You can do the 1 minus the probability that z is less than 2.5, or that's if I was doing both. Yep. Probability that z is less than negative 2.5. Either way. So remember the symmetries, right? So the thing that I always like to show students, right? If you want to see why these things are true, right? Here's 0, here's 2.5. We're looking for greater than 2.5. Because it's symmetric, we know over here at negative 2.5, these two shaded regions have to be the same. That's what symmetric means. And that's why greater than 2.5 is the same as less than negative 2.5. So whichever way you did it, what did it turn out to be?
0.0062.
0.0062? So in other words, how likely is this to happen? Not very. It's less than a 1% chance that you grab 100 people and have the average be more than 1 unit away, or 1 unit more than the actual mean of your overall population. And that should, again, that's the idea, right? We're starting to learn how we can start predicting what's going to happen based on how many people we sample. And the more people you sample, the better accurate you should be, or the closer to the actual population mean that you get. That's what you should expect. It should keep getting closer and closer and closer the more people we ask and the more people we ask. All right. So, that's 7.2. We did that one last time. Does this same concept work for percentages? So in other words, let's suppose that that we know at Blackhawk Tech, 10% of all students come to class with a hat on. All right? Sounds like a reasonable percentage, right? If that's the case, can we kind of do the same sort of a thing? Can we say, what's the probability that if we look at 50 people, that the percentage of people wearing a hat is more or less than, say, 12% or 14% or 8% or 7%, right? Can we play the same game? Of course we can, yes? Yes. The simple answer is yes, all right? Which you should expect, otherwise, exactly. We wouldn't do any of this anyways, and we could skip to the next section. So yeah, sorry, it definitely works, all right? So, if you have a percentage of a normal population, you can compute likelihoods for more or less than a percentage in a sample. And it works basically the same way, or a similar way anyways. All right, so the difference is that we are working with a p probability instead of a mean. A mu. But the concept is going to work roughly the same. So if we were looking for a probability that instead of having x's, now we're going to start dealing with p's. less than, I guess I should put a number in here, let's call it, I don't want to use x because that'll be confusing. Let's call it, and this tends to be the way the book call it, let's call it p hat. It's very common for statistician books to use variables that are the same letter but with like hats on it or bars over it to differentiate it as being something different. Again, don't worry too terrible much about it, but we'll play around with it a little bit.
Why don't they use different numbers or letters?
Hmm?
It's like the probability is less than the probability of something.
Exactly. And then essentially, yes. This is the probability of a probability less than a probability. Yes. It sounds insane, but it's actually what we're trying to calculate. Say the word probability in a sentence 3 times, you've got a kick-ass statistics sentence. The cool part about this is that we get to translate it into a z anyways. And the way the z calculation works is that you basically just convert the p into a z. And the way you do it is you are going to take p hat minus p, and you're going to divide by the square root of p times 1 minus p all over n. And I know that looks a little bit weird, but we'll do one example, and once you see it, you'll think, oh, that's what the hell you're talking about. Again, if you look on your formula sheet, you will see this formula written down somewhere, and you'll be like, huh? Okay, that's essentially what we're going to learn how to deal with here in a second. All right? So let's try an example, and let's even do the example that we talked about, right? So, if a BTC student wears a hat on average 10% of the time in class, what is the probability that, say, less than 8% of my students in a, let's keep it a relatively nice number, say a 100-person class wears a hat?
You're saying multiple BTC students, just not one singular BTC
No.
student.
So but there are 100 students, and what's the probability that less than 8% of them, of those 100 students, are wearing a hat? Okay? So basically, the 100-person class is my n, the number of students that I'm using as my sample, okay? Again, assuming that a student in my class would be a student that is a normal student. And sorry guys, I profess that nobody who takes one of my classes is normal. You guys are all weird. I'm okay with it.
How do you choose which P is one P?
Good question. Okay, so the key to this, folks, is that the P by itself is always the average, okay? So P is what the assumed population statistic is. And the P hat is what you are trying to see is more or less than, okay, of a sample. So P is population percentage. P hat is the testing percentage. So, what question did I ask you to do, right? I basically asked you, what's the probability that P is less than p hat 0.08. And you would say that normal p is 0.1, p hat is 0.08, and n is 100. And now apply the formula, right? P hat minus p. So when we convert this to a z, we're going to do 0.08 minus 0.1, and we're going to divide by that relatively nasty square root thing, okay? And this looks weird, right? P times 1 minus p. But just realize those are just numbers, right? If p is 0.1, what is 1 minus p, folks? What's 1 minus 0.1? So I often tell students to figure out what 1 minus p is so that you don't have to try and type that into your calculator because that makes it kind of a pain in the butt. So this is going to be the square root of 0.1 times 0.9 divided by the square root of 100. Or not the square root, straight up 100. My bad.
I was about to say, I'm like 2 square roots.
Not 2 square roots, just 1. Don't get over it. I like square roots, but I'm getting a little carried away. If you want to think about this in terms of what we were working on a little bit ago, basically when you're working with probabilities or percentages, the standard deviation of a probability distribution will always be calculated like this, as the square root of p times 1 minus p. And so if you think about that, sigma over the square root of n and you can absorb those all underneath one square root if you want. So what looks like some weird new number that I'm creating, the square root of p times 1 minus p over n, that is exactly the same as sigma over the square root of n. It's no different than what we were doing in the last section. It's just that sigma is defined in a weird way when you're dealing with probability distributions. All right, so now it's just a calculator problem. You got to be a little careful with the calculator because there's lots of crap going on underneath the. Divided by the square root of 0.1 times 0.9 divided by 100. Should you guys get negative 0.6666666666666? Close. And everybody get this. This turns into the probability that z is less than negative 0.67. Are we all good with making the calculator spit this number out? No, folks, you got this working? Right? Will? Uh-huh. There you go. Maybe you have in common?
I'm working. Slow. There we go. I got it. I don't know what I did last time. I must have did the wrong number.
What I often tell students to do just to be safe is do the subtraction in the numerator first, and then just use that one number. Makes it a little bit easier.
I just put that in parentheses.
Yeah. Works the same way. But if you do it by hand, then you one less, 2 or 3 less things to pick in.
Right.
Because it's not a hard calculation.
No.
Again, the key is sort of dealing with this square root that's a pain in the butt.
It's not a hard calculation, I just don't want to do it.
Again, this kind of calculation, folks, this is going to be common. The rest of the semester, you will be doing this kind of crap all the time, okay? Dealing with divisions by square roots, you do that in statistics so often that it should become second nature for you to do it, okay? That's kind of one of the reasons why people tend to hate statistics, is because they're constantly having to divide by something in a square root. And often, the stuff inside the square root is going to look like a fraction. And often this fraction is going to get complicated, okay? And so this really comes down to you guys starting to get comfortable punching these numbers in your calculator. It really does, right? The scary thing is that a lot of times people understand the statistics, but then just can't punch the numbers in their damn calculator. And that makes me very sad, okay? Because being able to work technology should not be what's holding you back from getting ahead in this class, okay? So you guys just need to practice and get comfortable with it, because yes, you're going to do it frequently.
What's the worst formula we're gonna have to deal with?
Worst?
Yeah.
You're gonna have one that's gonna look something like,
From chapter 8. So
there's one of them that's like p times 1 minus p over p hat 1 plus p hat 2 times the square root of n1 plus 1 over n2. This is all going to be over p hat 1 minus p. So something along those lines.
everybody else just have an answer, so we don't have to memorize that.
No, you will never have to memorize any formulas ever. Even if I give you a test in class, it will be open book, period. Or at worst, open folder with all of the formulas in it, okay? I do not want any memorization of formulas in this class. That is absolutely the last thing I want you to do, okay? I had to do it, but that was so stupid back then, it just pissed me off, right? So I'm not gonna force you to do it. If there's a nasty ass formula, you will write it down or have a cheat sheet for it somewhere, okay?
I don't even know how the hell anybody can remember these formulas.
You do them enough times and you start to remember them, that's what, or you're forced to cram for a final exam,
We
right?
had a lot of people crack back
Oh, yeah.
then, huh?
There were, it was a sophomore in college level class, and so it was one of those sort of weed out classes for math major. If you couldn't pass your probability and statistics class, that tended to say, nope, you should go be an engineer or go be a scientist or something like that, instead of a math position. And of course, I got to this and was like, oh, sweet. Because I was, weird. Anyways, so now once you get it converted into a z, now you can just look up the number in the table, and we're all good to go, right? So what is the probability that z is less than negative 0.67?
Oh,
Table A.
that thingy. I gotta open it up sometime today. 0.67?
Negative 0.67.
0.2514.
2514. So we would expect that there is a 25% chance, more or less, that out of 100 people, 8% of them or less would be wearing a hat when 10% of them normally do. Not bad? All right, now. there is a condition you need to test to make sure that this is a possible calculation that you can do. Basically, there are two conditions that you must test technically before you start doing all of those conversions. Okay, and if these two conditions are not met, you can basically not do any statistics on the problem. All right, so those two things must be true. If either one of them is false, your statistical analysis breaks down. Basically, the central limit theorem does not apply anymore if either of these happen, and therefore, if either of these are not true, technically you should do no statistics and just write down inconclusive. Okay? So before you do any tests with a probability, with a percentage probability, before you do it, take n times your percentage and n times 1 minus your percentage, and if either of those numbers are less than 5, immediately stop and say inconclusive. Statistics are not calculatable, or whatever the right word for calculable is.
I'm just gonna throw my book across here.
Well, no, this is like having, if you think about some of your earlier math classes, this is like when you have one of those questions where the answer is there is no answer. Yeah, no solution. This is the no solution case. If either of these things wind up being not true, you get to write no solution and stop. And that saves you from calculating a whole bunch of stuff where it was not necessary, or it wasn't going to do you any good. All right? So, either of these are false, then yes, you have to do both. Yep. And the central limit theorem fails, and our statistical analysis is worthless.
Bless you. Okay, good to go.
They always come threes. All right. Not bad. And again, I have often folks on a test, you will have one where technically the answer should be there's nothing we can do, right? And it's because one of these will wind up being false. Okay, so
What we just did, one was 90 and one was like 1, so that's right.
so one of them was 1.
No, it's kind of
Well, what's 100 times 0.1? It's 10. And this 100 times 0.9 is 90.
If you do it using
At the
10
square root.
times 1 minus 0.1.
1 minus 0.1 is 0.9. 100 times 0.9 is 90.
Oh, I thought that was easy. Wow.
Hmm?
Didn't I do it?
Yeah, it's 90. Right?
Yeah,
Is 90 more than 5?
yeah.
Yeah, so we're good. And what's 100 times 0.1?
Oh, it's greater than 5. Haha.
Yeah, it's
I thought
either
it'd
of
be
those.
less
Or,
than, I was like, oh, okay.
yeah, it has to be less than 5 for us to say we can't do it.
Okay.
Alright? So if my n had been, say, something along the lines of like 20, if my n had been 20, if there were only 20 students in my class, then you should have said this problem is not doable. Because what's 20 times 0.1? 2. 2 is not greater than 5, therefore, central limit theorem fails. I can't do any statistics on that sample. I need to have more students in order to have a good enough sample that my statistics will work. And that's that whole central limit theorem, is having enough of a sample such that you can guarantee true randomness. And that's kind of what this NP equals 5 does for us, right? It guarantees that we have enough of a sample that we can actually test the statistic we're trying to do.
So when we're on a test, do you want us to do this first?
Yes.
Show it? Okay.
Yes.
You just want us to-
Absolutely. Anytime you are asked a question to test the probability of a percentage, you should do this first, because if either of these are false, you can say, I'm done, I can't do it.
I didn't know if you wanted us to show that right away. Like,
Yes, right away. And then if both of these are true, then you continue forward and actually do the problem. All right? Not bad? Yeah, the panic happens when you actually have to do the homework and or do it on a test, right? So
yeah, like,
1 week.
I'm nowhere near ready.
Yeah, I mean I'm gonna give you the midterm exam on Monday next week.
Oh, before the midterms?
Well, no, midterm is next week. Midterm week is next week. So on Monday of next week, I'm gonna give you the midterm. And in theory, I'm gonna give you a week to do it. Right?
I'm thinking like the next week. Don't- You have to turn it in before the 26th.
I am perfectly happy as long as you get it to me before school starts up again. So if you want to take through spring break, you can, although I don't recommend it. I would hope that you would want to turn this in before the semester, the midterm week is over. So I would expect you guys to turn it in by like say Friday of midterm week. But I'm not going to force you to, because if life throws you a curveball and you've got 3 or 4 other classes and they all have a midterm and you'd rather study for those and say spend the weekend taking my test, that's fine. I'm okay with that.
How long is,
Sorry?
Probably
how long is the midterm?
Not.
How many months?
It's not short. How's that?
That works, I guess.
Yeah.
like 100 plus questions? or
No,
what?
no. I'm a jerk, not an asshole. Come on.
50 or more?
No, it's usually
Yeah.
it's somewhere like 25, but of the 25 questions, a good,
5 part.
yeah, a good handful of them have 4, 5, 6, 7 parts.
So technically, yes, there's probably plus 50 because each one is an individual question.
Yeah, babe.
I guess I'll lie to us.
25, yeah, right.
There's only 25 questions though.
Oh, Lord. I don't like being in class with Marshall.
But that, I mean, you should expect that for a take-home test where you have an entire week to a week and a half to do it, right? I mean,
And
Yeah.
also it's open book, and also you got all your notes, and also you spend a lot of time.
Yeah, but when you take it in the student side, they can't help.
no, they better not.
They can't.
They can't really help you anyway.
Yeah, I know.
Yeah, it doesn't matter. Because what is it? I had somebody went in there, is doing a class in there on college mathematics.
Mhm.
So I sent him to you. Like I told the guy, I'm like, look, find Marshall Monk because he will help you with it. And like the guy was so confused, and he asked the lady for help, and she's like, oh, no.
Well, yeah. I mean, there's some in there that are good. There's also some that are not.
Like for example, my kinesiology instructor, he's in there, but he's never there when I'm there. Like he's almost never there in the afternoon.
Yeah.
So I go to the other teachers, and they're like, yeah, I can't really help you. I'm like, oh, that's great. That's great.
All right. So, folks. Anyways, last section before the midterm. Yes. So the plan for Monday of next week is, 1, you guys get to ask questions about the Chapter 7 homework, okay? So I'm still expecting you on Monday to turn in the Chapter 7 homework. And so you're gonna get Monday to do free questions on it, right? So once you have asked me as many questions as you want over Chapter 7, then I give you the midterm exam.
Then the rest of the week is if your questions come in, otherwise no.
Yeah, on Wednesday, when we have class on Wednesday, the plan for me is to give you back your chapter 7 homework graded so that you can see how well you did on the chapter 7 stuff, so that you can correctly do the midterm based on your chapter 7 homework. Okay. Hmm? Well, I haven't graded any of the chapter 5 or 6 stuff yet either. So hopefully by Monday of next week, I will also give you all of your chapter 5 and chapter 6 homeworks that have been trickling in slowly but surely from all of you, right? I mean, there's still some people who haven't given me a chapter 5 and chapter 6 homework yet, so I'm assuming those people will do that soon.
Yeah.
Chapter
Each variable by and the other one. If we do a statistical analysis and it turns up a very small percentage, and then we multiply that times our population size, then it turns up, or it comes out being less than 5, do we go back and say that we can't do statistical analysis on things?
No. So when you get a really, really low probability coming out of your statistical analysis, that's fine. There's nothing wrong with that, okay? That just means that you're testing something that's not likely to happen. So as long as you have enough people to use the central limit theorem, which is what the NP and n times 1 minus p are greater than 5 gives you, that still applies. So once you have the first check of n times p, you're done with it. You'll never check it again. So your result, just because your result here, right here, was really, really small, right? So that one example we did where our probability was 0.0062, that has nothing to do with the central limit theorem.
So that only applies to the 7.3 stuff and beyond.
And it only applies, again, at the beginning, right? So even if this probability down here had been like 0.00004, unimportant. Because if I had picked a percentage here of p hat to be like 0.02, this number would have been really small. And as long as the regular data, right, again, it's p and n, not p hat and n. That's why you use p and n and not p hat. Because I can make p hat whatever I want, because it's what I'm testing against. So if I want to test against 0.00001, I can pick a really small number to guarantee that that doesn't work. So that, but that, again, that's outside the scope. The scope is driven off of what your population probability is and your sample size, period. All right? Okay, so approximating binomial case. All right, so let's go back to our 10% of students wearing a hat situation, all right? So go back to 10% of students wear a hat. I have, let's say, we'll keep it relatively simple. Say, let's suppose I have 150 students in my class. I have 150 students in my class. Then, what is the probability that less than, say 13 students are wearing a hat? Now, this doesn't look like a binomial probability yet. Okay, again, binomial, folks, is back to chapter 5.2. A binomial case would be something along the lines of, let's suppose I flip a coin 50 times. What's the probability that I flip 10 heads or less? okay? That's a standard binomial case that I could ask, all right? And the key here is realizing that this problem is very similar to that, right? Except that instead of the probabilities being 50%, 50%, it's 10%, 90%, right? And I can treat this case just like a regular old binomial case, all right? We actually could calculate this probability using our 5.2 statistical analysis for binomial probabilities. Totally doable, all right? But what I want to do is use what we just learned to approximate this using a continuous z case instead of going through that big, nasty binomial probability calculation that we normally would use, all right? So, instead of using a binomial probability, approximate this using z-table. All right, so how do we go about trying to approximate a binomial probability when we're using z-tables? Okay, it's basically saying take a discrete case, right, where we've got a fixed number of students, 150, and what's the probability that essentially, given that there's 10% of them, less than 13 actually show up, all right, with a hat. All right, so how do we go about approximating these things to do this? All right, so the key here. So one of the things that we need in order to use our z-tables is we need a mean for our probability distribution, right? And the probability distribution mean is just going to be calculated by taking n times p. And that should make sense, right? Because if 10% of the students wear a hat, and you've got 150 students, how many students do you expect to show up with a hat? 15. Or take n, 150, and multiply by 0.1. Makes sense, right? That's the same idea. All I'm doing is putting it into statistical nomenclature instead of putting it into our sort of mean and standard deviation type stuff. All right? The other thing we need in order to calculate our z's is the standard deviation. And the standard deviation of these probabilities is going to turn out to look like this. And again, the central limit theorem can prove that to you if you want to look at the proof. It's really ugly, but it's there for you if you ever want to. Just accept it at this stage. So use these two calculations to basically calculate whatever it is that I'm trying to ask you to do. All right? So for my example, folks, what is the mean? We've already done it. 150 times 0.1 equals 15. So we expect 15 students to show up with a hat. What's the standard deviation? 0.1. And what is 1 minus 0.1? 0.9. Minus 0.1. Again, you can do the 1 minus 0.1 in your calculator in parentheses, or you can do it in your head and just write it down either way. So somebody crank that number out for me. 3.674. Let's, for simplicity's sake, let's say we just round to the hundredths. Okay. Note, if I asked you to do one of these problems, I would tell you where to round your standard deviation to, okay? Because there's no standard set guideline for this. You could go 3 decimal places, you could go 4, you could go 2. Kind of depends on how nitpicky you want to be. And so now, we do this problem just like we were doing our chapter 5 stuff, or our chapter 6 stuff. I am looking for the probability that x is less than 13. I said less than 13, right? All right, now, here's where it starts to get a little bit funky, okay? No, it's going to be easier than that. It's even easier than that. Okay. Before we move forward, we have to consider the continuous case. So this is where these problems get a little bit on the weird side, okay? Because normally, when we were dealing with stuff back in chapter 5, it was really easy for us to understand what less than 13 was, because that would mean we had to have 12 students, or 11 students, or 10 students, or 9 students, right? It was discrete numbers, whole numbers. When we're dealing in the x and z world, we're dealing with continuous numbers, values that can be decimals, all right? And what we have to do is be able to handle those decimals correctly, okay? So we want our number to round to less than 13, where we might have a decimal point. So what values of x, when rounded, will be less than 13 if you include decimals? Right, but I want the lowest number I can get. That rounds to less than 13. 12.99 rounds up to 13. I want it to round down to 12. Actually, it's 4.99999999999, right? As long as the essentially, right, is less than 5. So to handle continuity, and this is where it's a little bit weird on this side, is that your less than needs to become this. Because x, if it can be a number that has a decimal, and it needs to be less than 13, it needs to round to whatever value it's going to round to, and be less than 13, right? If x was 12.6, where does it round to? It rounds to 13. Is it less than 13? No, right? 13 is not less than 13, okay?
I thought rounding was above 5, it went up. If it was
Exactly.
below 4.
No,
or if it was below
5 and above you round up, 4 and below you round down.
But then technically that's a rounded up number.
True, but I want it to be strictly less than 12.5.
Oh.
So I will never get to 12.5 because 12.5 is not included, that rounds up.
Oh.
Okay? So 12.4, okay. 12.45, okay. 12.49, okay. 12.499, still okay, right? But once I get to 12.5, I'm not, so I have to keep it less than that, right? So when you're approximating binomial with z's, you have to go from discrete to continuous and handle it correctly, right? Once you get this, now we do exactly what we did back in chapter 6. We're going to say, what's the probability that z is less than 12.5 minus the mean? What was our mean? 15. Divided by our standard deviation. What was our standard deviation? 3.67. And now all it is a straight z-table look. Six, eight, one, so rounds to 6, 8.
Well, it's 6, 8, 1, 1, 9, 8, 9.
Once you see a 1 after the 8, you're good.
Is it negative? Or did I mention something wrong?
Use your 12.5 minus 15. is
Better be negative. Right?
Oh, that's it. I'm so confused. What did I do wrong?
No, it is definitely negative. Right? So what is the probability that z is less than negative 0.678? Or sorry, 68, not 678. That doesn't make sense.
You're looking at
Point two forty.
What was that?
Point two forty.
So you want to do some quick review of chapter 5?
Sure. At least,
In other words, do this problem using the binomial calculation, the proper binomial distribution calculation. How would you do it?
Once you do it, I'll probably be like, oh yeah.
I'm just.
How would you do this using standard binomial? Standard binomial distribution from 5.2.
Go find an XL.
Yes, absolutely. Remember, folks, you are absolutely willing and able to use Excel if you wish. All right? No, I got no qualms about that whatsoever. Right? If you use Excel to get your answers, great.
Oh, yeah, that's so- that's what we're doing.
That's what we're doing.
I'm trying to think which one, like which lesson didn't record for you. That's where I was having issues.
Which one? I can't remember which one.
I think it might have been 6.
It was the end of 5 and the beginning of 6.
Yeah.
That I totally spaced off.
Pretty much I'm curious.
So how do we do it? So p equals 0.1, n equals 150,
Oh, so.
and I want to have probability that x is less than 13. So what would I have to calculate? In theory,
So total number, wait, are we doing the N of the X?
Oh, I don't know.
uh-huh,
Yeah.
remember these?
This is why I wanted to use Excel.
This is exactly why you want to use
Issues with
Excel.
Excel.
Because otherwise you would have to calculate 13 probabilities and add them all up.
Or in other words, with Excel, you just put in 12 and be done with it.
And say true to the
Sure.
cumulative piece of it, and then you can do it all in one step. But again, quick review. How would you calculate the probability that x equals 0, folks?
Brain fart.
Number, or the
Uh-huh,
total number of trials is N.
uh-huh.
Total number of successes is X, and the probability of success is the P, and so
Uh-huh.
then.
So what would it be? What should I write? What's the first thing I'm writing?
Probability.
Well, I got it. Probability that x equals 0. But I want to know, how would I calculate this number if I asked you to just do that?
Wait, what are we doing?
Binomial.
I know,
It was like 2 weeks ago.
P
I know, it was 2 weeks ago. Come on, guys.
N
That's not that far long ago.
Would it be 10%?
Nope, not yet.
So it's 150.
Yeah,
Because it's the same, or the
yeah.
total
What's the
number.
probability that if I have 150 students, that none of them are wearing a hat, if they are 10% likely to wear a hat? So it should start the combination of 150 things taken 0 at a time
Times
And
P.
then
times 0.1 to the
to the, 0.
to the 0th power times 1 minus 0.1 to the
0 minus x, which is the one, wait, with, yeah, what, x, 150 minus 0.
uh-huh,
There you go.
150.
Ah.
And that will be a very, 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 very small number. When you take 0.9 to the 150th power, it's not going to be a very big number. 0.9 to the 150th power? Oh, it's not that small. 0.0000000137. Right? It's not that small.
185 something?
Again, though, and then you would add combination of 150 things taken one at a time. 0.1 to the first power, 1 minus 0.1 to the 149th power, etc., 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 etc. And you could do every single one of those by hand if you wanted to. It wouldn't be impossible. It would just suck. Advice from the wise when you go to do this. Fire up Excel. We'll get basically 25%. It better be pretty close to 25%, right? Because that's what we calculated using the approximation, right? So we need binomial.
So if you need to answer
How
someone's
close
test.
are these approximations?
How close are they?
Like, is it a good way of doing these?
Let's find out. So number of trials. Or no, number of successes. What did we want? 12? Because we wanted 12 and down, right? Trials, 150. Probability of success is 0.1. Cumulative true. Oops.
Know that stuff in the beginning, right?
There we go. We got the probability by 0.25447. What was our approximation value?
2.4.
What was that?
2.3.
0.2483. So not as nice as I would like it to be, but rounded to the nearest hundredth, nearest percent, it's about the same. But I mean, I would have hoped it would be a little bit more accurate than that. But then remember, we rounded our standard deviation to only 2 decimal places, so it shouldn't surprise you that our accuracy is only to 2 decimal places as well.
So really, for the answer, it would just have to be within.
If you rounded it to 2 decimal places, I would grade it to 2 decimal places. If you rounded it to 3, I would grade it to 3. Hopefully, I would tell you where to round it to, and then you would know.
I'm sure I would miss that with all these numbers.
No way, we could do this.
No, I mean, I was misreading that in the instructions.
Oh, what's
So I just go gung-ho into it.
Please read the instructions, folks, please.
The editor's gonna say, you don't need to do the test, have a good spring break.
Oh, that'd be awesome.
We had to do that.
Are you gonna put which section each question is from, like what chapter?
No.
God
Are they
Yes.
gonna
Is
be
it
some
gonna be
type
in
of
order?
No.
damn.
This is part of statistics, is being able to read the problem and realize where the hell you're from. That's part of what you gotta do, alright?
So if we just failed this, I mean, we still got a good percentage to pass this class.
This is why you need to do well on the homework, or why I've been trying to convince you to work diligently on the homework, so that if you do happen to have a bad midterm or final, that your homework, which is worth more, will,
Thank God I'm not going into lab technician. This is just a class to get me my GI Bill.
oh no, this is real world stuff, folks. This is what's being done in the real world right now. I mean, these kind of calculations.
I bet.
Yeah, but if you want to get into a management or a high-powered, high-paying position, this is the kind of stuff you got to do, right? You got to crank numbers, right?
That's why people who are in
60%
business
of the class
have
is
great
70%.
hair.
Yes. I didn't say you weren't going to develop gray hair from this. I'm just telling you that if you want to get paid the big bucks, this is the kind of crap you got to be able to do and handle, right? I mean, this is what separates the guy who's, just sort of going to work versus the guy who's climbing the ladder at work. Take your pick.
I really do love how, like, truly makes you think of what statistics are being, like, especially from just chapter one, like what statistics are being, like I heard the dumbest statistic yesterday over Facebook, and it's like 95% more dog attacks than snake attacks. Why would that be? Why would that be? I don't know.
Maybe because there's
increases your chances of drowning.
Owning a pool increases your chances of drowning.
funny how that works, eh? I don't get it either. Darn reality, I hate it. Alright, so not bad. Now, before we call it a day, let's do one more just to be safe. Alright? Alright, so alright, so same problem. But this time I'm going to ask, what is the probability that at least 16 students are wearing a hat?
What are we, keeping the 10% and,
Staying the tape, 150 students, 10% probability of them wearing a hat. All of that stuff has stayed the same. But now calculate what's the probability of having at least 16 students to wear a hat. So initially, folks, what are we working with? What are we, in theory, if we were working in the binomial case, x is greater than or equal to 16, right? Because at least 16 means that it can be 16 or more, right? Now, that's the binomial case. What I want you to do is handle the continuous case. In other words, put this with a decimal point, such that it rounds to be greater than or equal to 16 with a decimal. In other words, I want the smallest number that will round up to 16 because it needs to round up to 16 or higher.
15.5.
Not 1.5, but 15.5. Because if my number, and I could put the equal sign in there, it's perfectly okay. Note that it doesn't matter, your probability never changes if you've got the equal sign in there or you don't. 1 point value in the continuous case does not change anything. 1 point versus a million points is meaningless. So, how would I do this using my approximation? Now you guys know it. What are you going to do? Z is greater than or equal to. What am I going to do to get my Z value?
15.5 minus, I don't know what our mean was.
15. Standard deviation did not change.
3.67.
One 362, so 1 4. Remember that that's greater than.
Do the 1 minus
You either do the 1 minus or
times the negative.
subtract less than the negative, right? Either 1 minus the probability that Z is less than or equal to 0.14, or probability that Z is less than or equal to negative 0.14. Either way you want to go, just make sure you do it right.
Wait, I'm gonna text my dude.
Yeah. what did that work out to be? 4443.
Are you money?
All right, now do this using the binomial probability distribution now.
So I think the answer would have been the 0.4443, right?
Yes. Alright, so we want greater than or equal to 16. The probability that x is greater than or equal to 16 equals the probability that x equals 16 plus the probability that x equals 17 plus the probability that x equals 18 plus
How about we do 1 minus the probability that x is less than 15? And then we use Excel to do that.
Great idea. That's exactly what I would do, right? The idea, again, is remember that this is equal to probability 1 minus the probability that x is less than or equal to 15. Because you know that Excel will do all of the sum for everything less than. It doesn't do the things greater than. Although we looked at the new version of Excel and it actually does allow you to do the other side in the new version.
It's a 2011 version, actually.
Yeah, which doesn't even, I mean, that just tells you how old this version is. I don't even want to know about it. But this is the idea. This is 1 minus the probability that x equals 0 plus the probability that x equals 1, not 0 again, 1 plus that, probability that x equals 14. All added together, and this you can do in Excel. So we can crank it out really fast and see how it works. Oops. Binomial successes, what did I want? 14? Is that what we were doing? Or 15? 15, right?
Or you did the 15.5.
And then remember that I have to do 1 minus this equals 1 minus A2. Ooh.
And that's true, right? We put true on that one?
Yep, got to put true on that one.
I prefer to go with maybe.
Which box was it?
The 0.43182. So our approximation of 0.4443 and the probability actual calculation is 0.43182. Again, not as accurate as I would wish it to be honest. But still within a certain amount of error. It's not too bad, but still, I'd be a little annoyed that it wasn't closer. All right, that is essentially it. All right. Whew. So for Monday, if you don't mind. Oh, sorry. Question?
Oh, just post the photocopies for chapter 11 again.
No, I have not. I will do that this afternoon. As soon as this class is over, I'll head to my office and do that for you. And like I said, on Monday, I will try and get back all of the homework. I plan to be in Monroe on Monday next week so that I can get you guys all your stuff back. And I will leave everybody's stuff here in a folder over there, and you can pick it
In
up.
that case, I'll probably be in Monroe next week.
Cool.
on it.